But you don't need to need a CID. So what's your team close? Something good.
No, anyway, I like pulled up my notes yesterday, and it was like the newest stuff. I'm like, what's this? So then it's like scrolling down. It's like, it's down here. So just like randomly for a day, it was like, oh, you want to take these things in here. Sit down here. Also, just like all the notes, how they correct this. You say, it's not bigger.
Should I get started? All right, welcome everyone.
Hopefully you saw an email from me, but just tonight we have this Flagstaff retreat. People see my email. Outside of pictures, outside of C4C at 5:45, and take us up there. It's about 25 minutes. And you know, if you want to hike up or run up, you're welcome to do it. Probably better to do that up than down. Well, okay, depending on your perspective. Because we'll be there till dark, so sketchy. Yeah, so that's it. I hope you all will join us. It's a pretty nice location and, you know, fun place for pictures and just looking around and hiking around. Okay, so yeah, so make sure you're on that bus.
All right, everyone, let's get started. So I basically gave a very, very broad brush overview of the field. I don't think we really covered much. I think today, let's get serious. So let's try to do some actual calculations, a bit more in-depth stuff. So so that's the outline of the lecture. So at least we have some sense why it's an interesting question. Although maybe I did not describe how to kind of answer several of the questions I posed yesterday, and so let's make progress on some of those things. So let's first start with an example where we can see this notion of separable mixed state, or the absence of it being separable, very explicitly. So that's the first thing. So consider a 2-qubit system. So let me write down the density matrix. So this is so consider the following state. I will call it RhoW. W stands for Werner, who introduced such states. I will define everything, but so psi minus is a singlet state. So with probability x, you prepare a singlet state, and with probability 1 minus x, you prepare just the identity, which has so we want to understand. So the question is, when is RhoW separable? That is, when can RhoW be written as where A is the first qubit, B is the second qubit? So that's the question we are asking. Is the question clear? All right. So let's consider two different limits. So consider as a function of x. So when x is 0, clearly it is separable, because identity you can always express in some product basis. So this is separable. And when, so this is 0, this is 1. And when x is 1, we know it's just a pure state, and it is clearly not separable, because it's, in fact, it's a maximally entangled state. It has entanglement entropy of log 2. So the question is, what happened in between? So to answer that question, let me employ a tool, which brings you to the second part. This separability implies positive partial transpose. So this is an interesting idea, very initiated by Paris and Hordesi. So the idea is the following. So if a state is separable, so let's write down density matrix in some a bipartite density matrix as say. So if rho separable, that implies that rho is rho I8 tensor rho IB with some probability coefficients. PIs are all positive. So now let me define what I call a partial transpose of a matrix. So let me first define for a most general matrix, then we will come back to this. So let me write this here, the partial transpose of a matrix. So if rho is in some, so choose some basis of rho. So I'm expanding rho in some basis for Hilbert space A and Hilbert space B. So we define partial transpose over B as the following matrix. So either you can interchange basically B and B prime here, or you can interchange here, one of them, choose the same, just the dummy index. Don't interchange both of them, you'll get back the same thing. So let me just write it as, let's say, prime. So I've interchanged it here. So basically, you're doing transpose only on the Hilbert space B. That's why it's called partial transpose. So far, so good. So I've just interchanged this this B and B prime here. That's what I did. So now, if you only saw this equation someday, and you did not see the symbol, and you walk into some physics department like Blackboard, you will think someone made a typo, right? I mean, but this is that's the whole point. This is something very some funny looking object. So this is not obviously a density matrix, and in fact, it generally is not a density matrix. It's still a Hermitian. So this is Hermitian. You can check, but not necessarily positive definite. Okay, but now let's assume rho is separable. Then what happens? So then partial transpose is easy because it's already written in a product way. So then rho partial transpose is just pi but if so rho IB is a density matrix in itself, right? Because that's the whole point of this statement. Partial trans so the partial transpose of B is just partial transpose of this object, because this is the whole all of B. So partial transpose, the transpose of a density matrix is a density matrix. So this is still a density matrix. By this I mean this whole thing. So this is one of the small exercises in your lecture notes to show that a transpose of a positive definite operator is a positive definite operator. Okay, so that's not very hard to prove. So this implies that this implies that rho partial transpose is a density matrix, is a valid density matrix. So this implies this. So that means negation of this implies negation of this, right? This symbol means not the usual notation. So if we take a partial transpose and we find it's not a density matrix, then we for sure know that it's not a separable state. So let's use that idea here to at least get some sense of even before we do the whole thing let's make our educated guess, right? So when you're close to zero, so there are three possibilities, right? Either this whole regime is non-separable and only x equal to 0 is separable. Other possibility is that only x equal to 1 is this whole thing is separable, and a third possibility, there's a phase transition in between, right? There are just three possibilities. So it's easy to kind of intuitively see that there has to be a finite regime around it where it is not separable. Why is that? Because at least intuitively, there is when x is 1, when it is a well paired, then we know that there is a bell-like inequalities which are violated by order 1. So if something is violated by order 1, it's hard to imagine that doing some tiny perturbation on it will suddenly change that violation by order 1, right? It's a finite body system. We don't have such phase transitions of, I mean, things have to be at least valid up to some regime. But it's not obvious that this regime, I mean, this does not extend all the way up here, because there is always some non-zero component of this. So how do we know that it is not just entangled throughout? So okay, so let's just at least find a bound for up till which point we know it is not separable using this criteria. So the fastest way to do partial transpose is to write everything in terms of poly x, y, z operators. It's just easier. So actually, Leo, can you actually help me with the? I think I will. It maybe we can do that. I have a bit of a injury. Sorry. So I will. We can do all 3 of them in one go. Then, or should I leave that? What do you think? I mean,
No,
okay, yeah. All right. So, so let me first write down this density matrix using poly x, y, z operators, and then we can see how to take partial transpose. So you can convince yourself RhoW can be written as identity over 4. Thanks so much. So minus x over 4, x1, x2. All right. So this is not very hard to see. The fast ways would, I mean, if you are just as a general trick to find such decompositions, if you write, let's say, rho as O are some operator, O is a complete set of bases for all operators. Alpha O are some coefficients. You can just take trace on both sides, and O is orthonormal basis for the operators. So trace of rho O, and choose a normalization so that trace of so that it's trace of O squares is let's choose it to be trace of identity, which is the dimension of the whole Hilbert space. So that will be just O alpha O times dimension of the Hilbert D times alpha O. D is the dimension of Hilbert space. So then alpha O will be average value of O divided by dimension of Hilbert space. So then so this implies that rho is just O average value of O D sum over all O. So this is a very fast way to write down any density matrix. It's just multiply a operator times its expectation value divided by Hilbert space dimension, and you can check that this works out this way. So now let's take partial transpose over qubit 2. So because A and B are 1 and 2. So what is a partial? Because this is a tensor product again, right? So we have to only take partial transpose of on the second one. So what is transpose of poly x? X, great. Let me not write. Keep writing tensor. It's implied always. So so what is partial transpose of y? Minus y. Great. So this is it. So now the question is this a valid density matrix or not? So the interesting thing with this state is like a state, everything's of x1, x2 commutes with y1, y2, which commute, all these 3 operators commute. So they are like numbers, right? So you can call this. So if you call, let's say, x1, x2 as some Ising variable s1, so this is plus 1 or minus 1. You can call z1, z2 as some Ising variable s2. So then y1, y2 is just minus s1, s2, just from polyalgebra. So then the eigenvalue of is identity over 4 minus x over 4, s1 plus s2 plus s1, s2. So these are the four eigenvalues, and s1 is plus minus 1. So now you can plug this in and you can check, you get 3 eigenvectors. I mean, so you get one plus x over 4 with degeneracy of 3. So this is 3 eigenvalues. And the fourth one is 1 minus 3x over 4. So these are the 4 eigenvalues. Okay, so now you see that when x is bigger than 1/3, this becomes negative. So this shows us that that bound there. So at least up till x equal to 1/3, it remains not separable. We don't know what happens after that. Maybe it remains non-separable even after that, but at least we have a bound now using this criteria. So it turns out for this 2-qubit problem, this is not only a necessary condition for it being separable, but it's also sufficient. So it turns out for Hilbert spaces, total Hilbert space of bipartite up till 6, either 2 times 3 or 2 or 2 by 2. This is both necessary and sufficient condition as proved by Hordesi. So then we know the answer. So there is a phase transition. So then the answer is basically, so this is not separable, and this is separable. This is x. Yes. No, that's why I just said that. I said that it's a generically, as I said, it's a if it is separable, then partial. But I said for if you have Hilbert space dimension up till 6, it's both necessary and sufficient. So right. So here's one exercise in the node where you are supposed to show that this separability criteria, I mean, something being separable is not a property of just its eigenvalues. It's a property about eigenvalues and eigenvectors. So you have to know the full density matrix. It's not, so if I, for example, if I give you partition function of some stat max system, it's not sufficient to tell from it it's separable or not. So that's why it's a more interesting object. It really knows about more internal, I don't know, quantum structure of a density matrix. So you can easily construct examples where there are 2 density matrices which have same spectrum, but one is separable, the other is not, and so on. Yes.
Why do you emphasize that the separability is not a function of the spectrum? I think it's also the case even if it's pure state, right? Or in the pure state, it is a function.
I mean, pure state is nothing about spectrum. It's a pure state spectrum is just one. There's only one eigenvalue. There's nothing about spectrum of a density matrix for pure state. Spectrum is trivial there. There's only one eigenvalue, 1, and the rest is 0.
Oh.
Yes. Can you speak? Right. So that's what will come. So how to quantify how much it is non-separable, right? That's what you're saying. So that's why we need entanglement measures. So which will come to that. That's one of the, I don't know. Okay, it's behind that the list of plan, but so we will come to that. Yeah. But at least it's a very, very powerful tool, right? It's still, if you can tell something is separable, that's a big deal. I mean, given so little is known about mixed state entanglement, that's why I think, or yeah, I mean, or at least you can tell when something is not separable using this criteria. So that's pretty powerful. But I understand that how much it is not, it's you have to ask those kind of questions, and that's why we will define entanglement negativity, which tells you how much it is not, and so on. So, okay, so so in this whole operation, poly y has some special status, right? So you might think that sounds a bit asymmetrical, right? What about y? I mean, just but the so the right way to think about this partial transpose is like doing partial time reversal. So you're so time reversal is an interesting symmetry, as you know, in quantum mechanics. It's not a unitary symmetry, it's anti-unitary. So because it's anti-unitary, you can't apply it on a subsystem while remaining the whole system to be a valid density matrix. This is the kind of obstruction when we talk about gauging time reversal. Like often we like if you have some symmetry, let's say we want to gauge it often, right? This is a very useful tool in condensed matter. So then, if you have time reversal, gauging it is really hard, and that's related to this fact that once you do partial time reversal, because gauging requires defining symmetry locally. So if you can gauge it, you can certainly apply on some subsystem without applying anywhere else, that action of that symmetry. So the fact that density matrix does not remain a density matrix under partial time reversal is related to the fact that time reversal cannot be gauged. So this is actually, I don't know whether I don't think this has been exploited much, this fact, but one can imagine finding other symmetries which are not possible to gauge and finding other ways to, other diagnostics of mixed state entanglement. For example, there are systems where the anti-unitary symmetry acts slightly differently. Maybe it involves particle hole also. Like if you're a fermionic system, maybe you don't take C to just, I don't know, C up to C down to minus C up, but you take C up to C dagger down, and so on. And so that could be a way to generate other maps which detect non-separability. So this is what was proved by Hordesi in very remarkable paper is that if you can find all such maps, by such I mean maps which when you apply on the whole system, the density matrix remains a valid density matrix, but applying it to a part of a system, it necessarily, it need not remain a density matrix. So those maps are called positive maps that are not completely positive. So this is the idea. So this is positive maps that are not completely positive. The partial transpose is one example of such a map. And the remarkable theorem proved by Hordesi is that if you can classify all such maps, the space of all such maps actually gives you a both necessary and sufficient condition for something being separable. But unfortunately, this is a very hard math problem. I don't think much progress has happened since Hordesi wrote paper in 1990s. I think it's still a very hard open problem in math, classifying such maps. But at least, okay, just to kind of get started, one can start poking around with symmetries which are hard to gauge and maybe find some new things. All right, so on a related note, you can ask another way to define time reversal is the most maybe the usual way of defining time reversal is that you take x to minus x, z to minus z, y to minus y, and of course I to minus I. This is also time reversal, right? The way we defined above was just y to minus y and I to minus I. So you can check that this actually does not give you a new information compared to this one. Although this is more nicer looking, but I think my understanding is it was not considered because it was probably realized that this is, the reason you don't get new information from this is because this can be written as a composition of this with some unitary transformation. So the unitary part doesn't do anything, so that's the reason. Yeah. Sorry? The unitary transformation you're asking? Yeah, unitary transformation is just take x to minus x and z to minus s rotation to y. Yeah, exactly, by pi. Yeah, and I to I because it's a unitary. All right. So where are we now? So there is something I wanted to mention about entanglement witness, but I think I will skip that for now. We will, if we have time, we can come back. So the next thing I wanted to mention was maybe sort of a review statement, which I mentioned before, but let me just mention it once more. When we think about few body system, like all the work in 1990s, when we were thinking about separability, they were really kind of talking about something being exactly separable, that rho takes that form, pi rho ia rho ib, right? But when we have condensed matter systems, things, for example, when we talk about pure states, a pure state is unentangled when you write psi as, let's say, phi a tensor phi b. So this is zero entanglement. But when we discuss many body systems, it's very hard to get zero entanglement. You always are somehow, often you have short distance entanglement, like area law entanglement, right? Because you can start from such state and apply a very short depth unitary on it to generate a short range entangled system, right? So morally speaking, that state is also kind of like a boring state. It's not much entanglement there. So in the same spirit, one would want to define short range entangled mixed states, which are nearly separable. Like, I mean, up till you did such some small amount of evolution on each of the element in the ensemble. So if one can write rho as pi, where each psi I is short range entangle, which I'll mention a few more words, but I mean that, then we can call, then we will call rho as a entangled mixed state. Now, the most kind of the easiest case to consider when what do you mean by short range entangle is that if you don't have any symmetries, right, then we just start from a product state, apply some finite depth unitary without worrying about what the symmetries of that unitary are. Then we call that thing short range entangle. But we also sometimes we want to qualify that statement. Suppose there are some symmetries, let's say some. For example, in the case of pure states, we talk about SPT faces, which are nominally short range entangled, but once you impose the condition that this unitary you apply on a product state, so you have some product state, you apply some unitary. If you're only allowed to write U as product of local gates, where each local gate commutes with some symmetry generator, then if you can write down wave functions which cannot be obtained using such a protocol, right? These are called symmetry protected topological phases, where the wave function cannot be obtained by a short depth U, where each U is a product of UI, where each UI commutes with some symmetry generator US. So one can then define similarly ensemble of such things which are non-trivial in this sense that you cannot do this. So you can call that long-range entangled SPT phases. Although there are other ways of defining it, as recently discussed by various groups, but this is, I would say, this is maybe closer to our definition here. All right. So, but I would not get into symmetries. I still think that there's a lot to understood and a lot to be understood in that context. So let's forget symmetries. So then we are allowed to apply any U with some, at least for now. Okay, we will, yeah. So.
You are allowed.
Yeah, I just mean short depth. So let's say, or something which doesn't scale with system size. That's all. Yeah. So the depth of the circuit, you have some I don't know, you have some initial state, then you apply some u where this depth is order 1, does not scale with system size. So not like log L, you can call that like long range entanglement. What about log of L? I don't know. But I mean, you can ask those questions, but let's just say order 1. I'm not defined negativity so far. No, I just defined that. I just showed that when something is not separable, right? Now we will define negativity very soon. But
Okay, so then my other question is, what about a test for that separability of a density matrix, mixed density matrix? Like looking at purity of some other measures. That's the purity you could have.
purity is not a good measure. So you want you want some measure which, for example, here
You could ask about how purity changes.
no, purity is not helpful, right? Suppose I give you just consider a classicalizing model at finite temperature, right? It's not pure,
Right.
but it has no entanglement. So purity does not capture the fact that something is entangled or not. This is a simple example, as you can see. Purity only tells you how much not mixed it is, right? But it does not tell you whether that mixed state is separable or not.
No, but you could do, right, but what I mean is, you could do the same thing that you do for pure state where you integrate, you trace over A, the complement of A, and then ask, and then you see you start with a pure state, you see the purity goes down.
Sure.
What happens if you do that for RhoW? Like you trace out compute purity of
Which RhoW you are talking about?
RhoW. Let's take a separable RhoW and non-separable.
But okay, but so you're already starting from a mixed state and then doing partial. Then you're doing
Yeah,
integration.
I want to know maybe the purity of RhoW. I can't figure out in my head, but purity of RhoW changes in a different way.
But I think in both cases it will be non-pure, right?
I know, but maybe the way it changes is different.
Yeah, I don't know the answer. Yeah, I mean it could be, but I think
The
the
philosophy is the same. Rather than changing purity from one.
no, but I think what we are after is something much more stronger. We want some at the very least, if you want to define some measure, it should vanish on separable states. It should be just 0.
Well, yeah, so I can't tell if it's the purity.
Yeah, but just take this example, right? This is a mixed state. You can trace out some region, but it will still have non-zero purity. So it just, yeah, I don't think it's as easy as calculating purity. So
Question. So here we'll say Shortrange, you mean exactly the same thing as area.
if it is if it is Shortrange entangle, then it has area law, yes. But area law does not mean Shortrange entangle, of course. Shortrange entangle means area law, but other way around is not true, right? You can certainly have long range entangles here which have area law. All right, so okay, so we at least define, okay, what do you mean by Shortrange entangle mixed states? So now let's define some measures of entanglement which try to capture how much it is not like that. So so what would one like from a measure? We would like a measure to be good. I mean, it's a good measure if it vanishes for a separable state. That's like I would say the minimum, but one would like probably more things. For example, one would want it to decrease under LOCC operations, which is very useful, I don't know, thing to do. In most, I mean, certainly it's true for pure state measure, the monomer entanglement. So one would like that criteria, and the third criteria, which is harder to satisfy by some measures, which may sound like a very obvious criteria, which is don't say if it is separable, it vanishes. Say if and only if it's separable, then it vanishes. So that's called faithfulness. And that is not satisfied by some measure, for example, negativity. But they are measures for which it is satisfied, but they are very hard to. We don't know how to calculate them for many body system in any kind of algorithmic way. So now let's let's define these measures. What should I erase? Let me just erase. Do I want to keep that? Let me keep that. Yeah, keep that. So let me define three different measures, which one is just negativity. I mean, let me call it entanglement negativity or logarithmic negativity, just the name. Also called. So this is defined as, let me call it just En, then some notation is one norm of the partial transpose. So what is one norm of a density matrix? So the one norm of a density matrix is where lambda I are the eigenvalues of log. No, sorry. So the log, sorry, thank you. Yeah, so if you don't take log, that was initially called negativity, and logarithmic negativity is log of that. Thank you. So and the one norm is just the sum of the absolute values of its eigen. Sum of the modulus of the eigen values so the right. So if the state is separable, then we, as we just argued, that rho partial transpose is still a valid density matrix. So one norm is, because then you can drop this mod because all eigenvalues are positive. So this is just become 1 because a valid density matrix. So then log of 1 is 0. So it vanishes for separable states. But again, if it vanishes, it does not mean it is separable. So it's not a if and only condition. It's a if it is separable, then it vanishes. But if it vanishes, it does not mean it's separable. So all right. So there are many different measures, and it's possible one can define something using purity. I've not tried it, but maybe Leo will cook up something which will work. But I don't have anything right now in my head using purity. But the other two which are quite well known, one is entanglement of formation EF, which is defined as so first you consider all possible such decompositions, rho as pi psi I. So they are infinitely such decomposition in general, and for each of these psi I, entanglement is a von Neumann entanglement is a good measure of bipartite entanglement because it's a pure state. So you can define from this SA for psi I, which is trace of rho AI log rho AI with a minus sign, where rho AI is just the, let's say, trace over B of psi I. So then you can define an average entanglement for one such decomposition, which is PI SA psi I, some more I, and EF is defined as minimum of over all such ensembles. Yeah, if you were writing a math paper, you will probably write infimum, but I'm not doing that. Okay, so
possible that because the optimal one is that say can find a realization everything is a price thing. One of them that is more than a price thing.
Right. It's a good question. I've thought about that a little bit, but I have not found very natural examples like that. Maybe contrived examples one can cook. So then from a point of view, for example, entanglement or formation, it'll be just zero almost, because like unless there's some delta function there, right? If it's like almost uniform distribution and only one of them, let's say there are sum of million things, only one of them is non-trivial, then nominally, I mean, from the point of view of separability, it is not separable, but from point of view of entanglement or formation, it is almost there. Yeah, but I don't know, very natural. Like, I mean, I tried to cook up something once, but I don't know how they naturally arise. Yeah, but maybe you will find something. Yeah, it's not. So I was coming to think, yeah, next, sorry. Yes. You have a question?
Oh, yeah. So is the entanglement equality is it positive?
So because it's log, okay, does it have to be positive?
Raise it above 1.
Yeah, I think it has to be positive. Yeah, right. Because this is bigger than sum over all I lambda I. So which is equal to 1. So log of bigger than 1. It just anyway, just the name. So it's just capturing how much partial transpose is not a positive definite. So yes.
You just said that the negativity is not a physical measure. I'm wondering, in practice, how much do people worry about?
I mean, not as much as they should probably, but I think they could be. I think the part of entanglement which is not captured by negativity is that's called bound entanglement. It turns out that entanglement cannot be easily distilled into EPR pairs. So you might say, okay, then maybe it's some short range stuff maybe, but I don't think people have thought about it in any very systematic way so far. Because I think one interesting question, at least for me, that I would like to think about is that, are there cases where there's a long range bound entanglement, long range part of entanglement which is not captured by negativity? And I don't think any progress has been made on that. So sorry? Minimum over all such decompositions, over all possible decompositions. I think I just said in words. So this is, we don't know how to calculate this efficiently, as Vedika just pointed out. So the only thing we know is if you have 2-qubit system, then we know it exactly. If I give you any density matrix over 2 qubits, and you are interested in entanglement between the 2 qubits, then there's a closed form expression for it. And then there are special cases when there's for many body system, there are special cases where it can be computed. But those are cases when there's a huge sum symmetry, either some permutation symmetry or something like that. And we also found an example with Shortrange, which was just mean field like models. When you have things like spherical models or all-to-all coupled models, there also we could find an example where there's a upper bound we found on EF and we found a lower bound and they matched. So it was somewhat like a interesting coincidence. Yes. Yeah. So I would say most things are like that. I mean, at high enough temperature. So there's something called sudden death temperature of negativity, above which it exactly vanishes. And but there's no reason to believe that's where the whole entanglement vanishes. But that temperature tends to be ordered in most systems, that if it asks what is that temperature, beta is almost like when your thermal length scale is almost order of the lattice scale, that's when it's sort of, at least based on our field theory understanding of that temperature. So that's why maybe people don't worry about it, because you're already in the limit where, I mean, it's almost a boring state. Yeah, I was thinking about the Gibbs state. So take a Gibbs state of some lattice Hamiltonian. There's something called sudden death temperature. I wanted to mention all that, but where the negativity vanishes above that temperature. the most, like, I mean, suddenly in the case of bosonics, like spin system, that happens. There's a way to define fermionic negativity as defined by Chinchilla and collaborators. I don't think there is a certain dead temperature, but it's a slightly different definition. Yeah. Yes. Separability. That I'm saying it could still be not separable. And they are, so they are for the few qubit system, they are very simple examples. So where we know exactly, you can find some more stricter version of entanglement, notion of which some other measure, which is, I mean define it, but you can show that it is not separable, but negativity is 0. So those are called, that's called non-PPT entanglement. That's a name, like, because it's not kind of hidden in the, it's not kind of, yeah, it is non-positive partial transpose entanglement. So then, yeah, one very nice set of results there were something called, this is really getting into maybe details, but it's something called unextendable product bases. This is a very cool idea developed by various people in 1990s, where so if it is separable, then you can show that it's the range of density matrix, which is the range of a matrix, is the span of its eigenvectors. I mean, I mean, yeah. So then you can find cases where, so if the density matrix is separable, first you can show that there exists a product basis in which you can expand it always, and then you can find examples where there is a product basis which is incomplete, and then you can find that a density matrix has a support on this orthogonal subspace to product basis. So this is called unextendable product basis, unextendable product basis, and that's one way to generate interesting entangled states which are non-PPT. Yeah, I'm happy to send you reference if you're interested. But all right, so okay, so now, so we've defined negativity, we've defined entanglement formation. So this is okay. But the next thing I will write down will make this look easier to compute. Okay, so but that's the nicest thing we know so far in terms of its properties. So because entanglement formation, at least you can start doing some maybe optimization. People have tried playing around with various optimization techniques to find it, and there's some bounds you can find sometimes. Yes.
Is that a faithful measure?
Yeah, so the EF is faithful measure. So I will write down 3 measures, 2 faithful, 1 unfaithful. All right. So the third thing is squashed entanglement. So I'm not writing any references here. These are like famous papers from 1990s, early 2000. I mean, that's why I wrote down the notes. You can find some references there, or look at the review article by RhoW. And all right, so this is defined as so you're given some RhoAB. So consider all possible RhoABC. So you enlarge a Hilbert space such that trace over C of RhoABC is RhoAB. So this is a sorry, no, this is not a purification. That's the main point. So this is a that's I mean, that just slips out sometimes, but this is a what do you call extension of this density matrix. So this is not necessarily pure. So that's why this space is just unimaginably large. The only condition is this. And then look at the conditional mutual information between A and B. So look at, I don't remember the symbol I use in my notes for conditional mutual information, but let me just call it E of A, entanglement of A with B given C. So here we will use just the von Neumann entropy to define this. So this is S of SAC plus SBC minus SC minus SABC. And your squashed entanglement, E squashed, is minimum of this. There's a half, I think, here. So this is what is called squashed entanglement. And so I don't know how many have seen this combination of things. This is what enters in strong severity. So this is always positive. Anyway, so this is very difficult to calculate, as you can imagine, but it has some of the nicest properties. Despite being we can't calculate it, but we can use this definition to and people have used this definition to show its very, very interesting properties. It has all the good things you will want from a maser. It vanishes for it is faithful, it's entanglement monotone. But one very special property of this, which is not known to be satisfied by pretty much any other maser, as far as I know, is the monogamy condition. So that's basically, so entanglement of A with, let me make sure my notation is the same. Okay, I think let me keep column with B1 to Bn. By this I mean union of B1 to Bn is bigger than equal to E squash A with Bi sum over all I. So this is called entanglement monogamy condition. This is the definition of monogamy, and this is satisfied by squashed entanglement. Yeah, and there are a few other properties which are very interesting, but okay, these are some of them. Yeah, of course, that's satisfied by all three of them. So that is like the very minimum we ask. So, but it has much more than that. So, yes.
Question is only one question. I want to know whether this stays separable.
Right. Of course not. I mean, no. But I mean, we don't even know how to calculate it. So that's why we stick with this. So you won't be able to tell yes or no. But if you're using this, you'll be able to tell that if you find the answer to be non-zero, then you know it is non-separable, and this is computable. Not maybe this, maybe some rainy version of this. Even this, suddenly using, if you have tomographic techniques, you can go and do it, right? So this is the easiest one. This is done numerically all the time, and I'm aware of experimental papers which have also measured this or similar very related things like rainy versions of this using this shadow tomography. So they are, yeah. So progress can be made on this one. This is very hard. That one is very, very hard. Yeah. Right. No. I think so. Not to my knowledge. I don't think so. Yeah. Because we know there is entanglement of purification, which is almost like this. Yeah. I think so. Entanglement of purification is known to be not a good measure of entanglement. That's why we don't mean. Yeah. This is the definition of EF. Minimum over all possible decompositions of this quantity. Yes.
Why is monogamy something that we physically want?
Yes.
Why is it?
Because it's somehow, I don't know. It just makes sense. Yeah, I don't know. I mean, I think it is a. I mean, it's a personal question, right? About but what? No, I don't mean any in that sense. I mean just what properties you want from a measure, right? Not. It's not like a I mean, you define what has nice properties, so I can use it to do some interesting calculations or prove things, right? So we know for von Neumann entanglement, although you don't have that condition, but strong subadditivity is almost implies, I mean, strong subadditivity does imply monogamy in the, maybe in a slightly looser sense of the word, right? If A is highly entangled with, A is maximally entangled with B, it will have zero entanglement with C. That you can show using strong subadditivity. So that's a property of pure states, right? We use it all the time to argue all kind of interesting results in I don't know, pretty much everything we know about applications, like the interesting applications of entanglement to many-body physics. I would say more than 98% or something like that came from thinking about strong subadditivity, and whose its essence is like sort of like monogamy. So then, it's a very useful thing, but I don't know whether how easy it is to use it so far. If you can prove that it has certain features, let's say you find some interesting bounds or something, but if you can't calculate it, then it's hard to know what will you do with it afterwards. Yeah. Yes. Anything. Yeah. No, not to my knowledge. I think you have to look at basically everything. Yeah, I think with the size, it's something like, I think it grows very fast with the size of the Hilbert space. That's my understanding. Probably the whole Hilbert space. That's really my guess, but I don't know the answer. It's a good question. But that means my naive intuition is probably the whole Hilbert space. But because otherwise, when will we be able to make progress of, let's say, single qubit with million other things, and that we don't know. Yeah. Yes. Right. Because I mean, if you're extending your Hilbert space, conditional mutual information is precisely the kind of a measure of entanglement between A and B, right? Sort of, because you're canceling out all the, so that if you, for example, you can draw this simple picture. Let's say you have A, B, and C, just very in a very naive way. Suppose you have well pairs going between A and B, B and C, A and C, and so on. This is very kind of a simple state. So if you look at this thing, it will cancel out. This quantity is only sensitive to Bell pair shared between A and B. It will cancel out all the stuff between A and C, B and C, and overall A, I mean, some tripartite entanglement. That's why this is a good. That's why we use this, because it kind of cancels out things which are going from B to C and A to C and so on. All right. All questions? How much time? Okay, we have time. Okay, so now so this is all just definition, right? We haven't done any actual like many-body physics so far. So now let's start thinking about. Okay, so these are okay. EF is interesting. I think I still think more things can be done with EFs. I mean, I can at least imagine extending some of the results we know for EF now. Or, I don't know, some mean fieldish like states, but squash entanglement. Okay, maybe some of you will figure out, but at least I don't have much to say. If there's time for, if I don't know if by the end of next lecture we have some time left, we can maybe come back to this and discuss some examples where we can calculate this in some many-body systems. But for now, let's move on to focusing on negativity and its applications, because it does not require optimization. Okay, so now so that's why I kept this. So let's let's do one computation here. For the negativity, okay, let me just state it, right? This is a simple thing. We already calculate partial transpose, we got its eigenvalues. So now you can calculate its negativity very trivially, just knowing the definition. And you will find that it will, so if I plot negativity as a function of x, so I don't remember the way it states. So when x is 0, it is separable, right? So it will look like something like this. So at 1/3, there's a phase transition, it will arrive. So this find it goes to 1. Right. So and then I put some few more exercises for negativity. You can go and try calculating them. So the one property I should mention that it doesn't matter whether you do partial transpose over A or B. You get the same answer. Again, this is a exercise I leave that for you to show. It's not very hard to prove. Another property which I wanted to mention about negativity is if I give you now a pure state instead of mixed state, right? What is its negativity, right? But I mean that you have a pure state, you can still divide a system into A and B, do partial transpose over B, and define its negativity. And it's again a homework exercise. You can show that En for a pure state will be equal to Rayleigh negativity, Rayleigh entanglement, Rayleigh whatever the trace of square root of rho times 2. Yeah, so you can show that. That's again a exercise. You should be able to at least try it. I mean, and then if you get stuck, ask me. But it's not super hard. Yes. Yeah. Yeah. As I said, that for 2-qubit system, it's a necessary and a sufficient condition. So it doesn't matter. So if you look at EF, it will also be 0 up till here. Then it will rise. I don't remember whether it's exactly equal to this, but it has a similar plot. Yes. Yeah, but they are not eigenbases. So I will discuss some of them. So that will be the next. How do we kind of sometimes show something is separable to find the correct and unraveling? So that's in fact a very interesting question. And so in fact, I would say the most of the progress we have made is thinking about correct unravelings. So so I will discuss that for toric code and so on. Hopefully next lecture. And yes. Just writing rho as a sum of things, so sum of pure states. This just the name, yeah. No, you can do it, but I'm saying which one is the most helpful for finding bounds or showing something is separable and so on. For example, if we take, for example, toric code that take its thermal state, if you work in the eigenbases, each eigenstate has topological order, but we know at finite temperature, toric code has no topological order. So can one find such decomposition where each state is Shortrange entangle? And the answer is yes in 2 and 3D, and so I will discuss that. I thought there was a hand somewhere. No, okay. All right. So now let's come to. So now let me first focus on for at least half an hour, maybe a bit more on Gibbs states, because I don't know, Gibbs states are one of the most natural mixed states which arise in nature all the time. So at least good to think about them, think about it a little bit. It's entanglement. And it was also related to some comment I want to make based on yesterday's lecture. I forgot to mention. So I would say the first most, I don't know, interesting result, at least to me, is that one can show that if a Gibbs for a Gibbs state with finite local dimension on each side, negativity is area law. So the first result is by the rho is, so H is a local Hamiltonian. So this is the first result. This is proved in a paper by Hastings and collaborators. I don't remember 2014, 13, something like that. So the I won't prove it. It's a bit detailed exercise. It's in the appendix of that paper. So but I will give you some intuition at the very least. So but before even talking about the intuition, let me comment something on yesterday's lecture when we were talking about using entanglement as a probe for thermalization or lack of thermalization. So I had mentioned this, I had plotted something like this area law to volume law transition, right? So that also is very intuitive from this perspective, because when your region C is large enough, then density matrix is almost thermal. So then you expect area law for region. So this was, let's say, yeah, you know what I'm saying. I mean, we divided the system into C and AB, if you recall. So I'm just saying if C is large enough, then A union B almost looks thermal. So then you can kind of use this kind of intuition. All right. So that is one property. So let's build some, okay, at least some intuition. So if let's say H as, so there's some fine print here that we are assuming. So let me write H as HA plus HB plus HAB, right? You can always do this. Again, I'm always talking about bipartite entanglement, right? So I'm doing partial transpose over B or A if you like. So if HAB was 0, clearly rho is separable, right? Because e to the power minus beta HA, e to the power minus beta HB is clearly separable. So that at least gives some intuition that it's coming because of HAB, this entanglement. So that's why you expect something like area law. At least that's a naive intuition. So the fine print is that, let me make sure I say it correctly, is that the bound proved in this paper is that you write, for example, HAB as HJA tensor HJB. So these are just boundary terms. Some are all J. Let's say J goes from 1 to N. And each of these HJ, let's say product of HJA, HJB, norm of that operator. I don't remember what norm we are using. Probably it is the eigenvalue norm, wherever the largest eigenvalue is my guess, but probably doesn't matter. So then let's say this norm product, the product of these two norms is less than some J, then what you can prove is that En is less than equal to 2 times J times N. In fact, it is a slightly stronger bound. Okay, let me try to slightly, but it's same thing. It's beta times, okay, J N plus norm of HAB, which you can show is also less than 2 beta Jn. So J is the magnitude of these terms, N is the number of terms here. So there's a beta here, importantly, right? Because only at a non-zero temperature, this bound exists. If you go to zero temperature, we clearly know examples, right, where area law is violated. You can get logs or even volume law and so on, right? As recent work by Ethan and collaborators. So then, but this is for a Gibbs state, not for the ground state. All right. Yes.
Is it possible that the bound entanglement is volume law, even if it's negative? Some other
That's a great question. Sorry. So the question is, can the bound entanglement, which is not accounted by negativity, can that be volume law? I don't know the answer. The part of entanglement which is not accounted by negativity, so they are, as we discussed, they are states which have positive partial transpose but are still not separable. And if you, let's say, look at squash entanglement or something, my guess is no, yes, because of this, I don't know, because of the same intuition as I just mentioned, that if HAB was 0, it is separable. So bound entanglement is 0 when HAB is 0. So if you think about it, at least in some very naive way.
If you take like the beta to be small enough, like the temperature to be small enough to the gap, not exactly 0. You still have violations of some kind.
But that's like a different axis you're not taking. I'm talking about, you're asking about area law, not, you're asking area law at non-zero temperature, right? Let's just first maybe ask that question without taking zero temperature limit. I'm saying at any, when beta is order 1, if HAB is 0, it is separable. So then that at least suggests to me that even a faithful measure of entanglement will be area law. Okay, I mean, maybe there's a way to prove it. I don't know the answer. Yes. So for example, right, J is, you're just writing HAB in some, for example, suppose it was Heisenberg Hamiltonian. Let's say S1 dot S2, right? You can write it as S1x, S2x. Why I'm doing this? We are quantum information people, right? So should use XX plus YY plus ZZ. So then the N is 3 here. Yeah. Yeah, someone once joked that the biggest contribution of quantum information is like to condensed matter is quantum computing and this notation. Anyway. Any other questions? Oh, you have a question? Yes. I don't think it has been proved, but at least that's what we find in all examples we know of. Yeah. I don't know a simple proof why it should decrease, but maybe there is a proof. I mean, the bound certainly is like that, right? The bound is suggesting it is a beta there and so on. But I don't know it has to be monotonically decreasing. My intuition is it, at least if you assume like, yeah, I think it should, I think, but why do I think that? Yeah, as I said, there's a certain that temperature for negativity. There exists some temperature where it becomes 0. We can call it a phase transition for negativity, but I don't think, as far as we know, that has no physical significance. That temperature is like basically lattice scale, like beta is order A. So you just, for example, in a so that's okay. Let me point out on that note some results for negativity based on this. So I will, okay, what should I do? Where is that? So for example, let's consider some simple Hamiltonians, which we can, I don't know, which we all love and use all the time, like CFTs, Fermi surfaces, and so on. So I mean, the three most common things, like, okay, we always, I don't know, if you're starting to think about a new problem, right? What are the things you try? You first say, okay, let's try either CFTs, or you try free fermions, or you try stabilizer codes, right? These are the three most common things we try. Let's just look at them a little bit. So consider, let's say, CFT. So this is work by Eric, Tony, Calabrese, and John Cardi. So there you will find that EN looks like something like. So if you recall, in the what is the ground state answer, right? Ground state is C log L, right? So what do you guess now? What do you think what should happen to this object at finite temperature? It's not very hard to guess. Yes, great. Something like this. A is the lattice cutoff. So that's why when beta becomes order A, that's when you find the sudden dead temperature. Now, what about Fermi surfaces? So the thing is with fermions, as I mentioned in my small note, there are two separate definitions for negativity depending on how you do partial transpose. You can put some signs with fermions because they anti-commute. So there's totality there. The one I think is one introduced by Shinshir Ryu and collaborators. I think it's somehow, at least I think it has nicer properties, certainly computationally, but it also captures things which are missed by the other definition. For example, SPT entanglement. So I think there are good reasons to use it. And if you use that definition, where the one introduced by Shinshir and collaborators, you can probably again guess what should happen to recall what is the for the pure state. It's something like L log I mean something like this, right? So Kf is the Fermi momentum. This is also Kf importantly. So you can guess what will happen. This will get replaced by log beta. I mean, Fermi surface is essentially a bunch of CFTs glued together. So okay, so it should be something like log beta over A. So then, these are two things. Then, so now consider H, which is sum of commuting terms. So these are like your stabilizer codes and so on. Let's say toric code or something where so in this case, it's easy to kind of get intuition for the area law also. So let's just go through that exercise a little bit at least. So we want to look at e to the power minus beta. So sorry, this question. You have a question? Sorry. L is subsystem size, which is what define area. Just the boundary. Huh?
Find a jump only cuts off the bar.
Yeah, because there's the area laws we discussed. So area law is always there. So the L is the this length is L. So let's write this as the sum of commuting terms as HA plus HB plus HAB. So then, since it's a sum of commuting terms, you have so once you now if you look at the so this part is already a valid density matrix, HA and HB. This actually, so if you do partial transpose on this, nothing really happens. The partial transpose only acts non-trivially on this part. So once you do partial transpose. So now we want to put a bound on this, right? So the norm of, we want to put a one norm. We want to calculate negativity. So we want to estimate this object. There's a Z here in front. Z is the partition function. So this is En. So now we can use the fact that the norm of product of objects. So norm of AB is less than norm A, norm B. So then this is less than equal to e to the power minus beta. So the norm of, because this is a positive matrix, so its norm is basically, yeah, it's kind of trivial. So then some of its eigenvalues is just, if you like, a function of this region. So this is this divided by z norm of this times e to the power minus beta HAB partial transpose norm. So I'm just using triangle inequality. Maybe my handwriting is bad here, but I'm just saying, yeah. Anyway, so that there's a, so now if you look at this ratio, this is like the partition function of the bulk of the system divided by partition function for the whole system. So you can just add HAB and subtract it. So then this becomes 1 over e to the power minus beta HAB trace over AB. I mean, a trace over boundary, sorry. So that is trace over the boundary of the system. So then this is a ratio of, if you like, essentially two free energies, both of them for a system defined only along the boundary. Because numerator is defined, this is like a one norm of some exponential of something with some partial transpose. Even if this is not a density matrix, value density matrix, even then you can write it as e to the power something that something may not be Hermitian, but it is still some local object. So e to the power some sum of local terms which live along the boundary. You're looking at its partition function divided by some partition function which is defined for a system along the boundary. AB is terms which connect A and B, just to make sure this is A, this is B. AB only lives along here, HAB part. So this manifestly is area law. So this is one way to at least quickly show area law for a class of systems. Yes. Uh-huh.
The faithful method of entangle as well.
That's a great question. So I've tried proving that they don't, but I haven't succeeded yet. I don't think so. Yeah, but okay, this is just my guess. I think it may be a feature of few body systems. My naive guess is when you take thermodynamic limit, Tn will really basically infinity. That's my. I mean, there's a certain that will be basically goes to infinity. They're when I've made this argument, I don't know. I have some argument why that's the case, but the kind of statements I hear from people who think about this from more quantum information perspective, they say that the space of separable state is like a always has is like an open set. So if something is separable, there's always some nearby states which are separable. But I think there's a question of thermodynamic limit. So one has to be a bit more careful with that statement. Even if infinite temperature is separable, doesn't necessarily mean that e to the power minus beta h, where beta is almost 0, is still separable, because that open set may be kind of vanishingly small in thermodynamic limit, even if it has some state. So I don't know the answer, but it's a very, very important question. But I haven't really solved it. I mean, anyway, the things I tried was trying to see if you expand Taylor series expansion in beta, identity minus beta h, and try to see whether it looks like some sum of separable things, something like that. But I couldn't see a natural way to write it that way. So that doesn't mean it doesn't exist, but at least it's not obvious it should exist.
You talked many times about when beta comes close to the lattice spacing, but clearly you need to make some dimension conversion to compare this. What dimension conversion are you doing?
Yeah, and I mean, in a CFT, beta has a dimension of length, velocity.
I know nothing about CFT. We was in more general case.
There's some. I mean, for example. Yeah. Divided by velocity.
Physically, what the
thermal length scale. if you look at 2-point correlation functions, they decay exponentially with some length scale. You can call that the length scale, the thermal length scale, which in CFT is basically beta.
Correlation.
Correlation lengths for equal time correlation functions at high temperature.
The standard thing is like the slab is beta is far along.
Yeah, that's all. Yeah.
But generically, there's no reason really to compare betas with lengths unless you know that length scale like time. You have a diffusive system.
Yeah, in a CFT certainly it's true. Yeah. I mean, I was only writing some very specific examples here. I'm not saying this is true for every system. So,
The message of the board is that the examples, the non-trivial, the non-area law, zero temperature collapses for
yeah, exactly. And the intuition is always so the way to think about that is again, I think in purifying the system using some ETH like intuition. So if you had a non-zero temperature, think about extending the system to some C. So there's a lot of to get that thermal density matrix to begin with, there has to be large entanglement between AC and BC, and that kills off the entanglement between A and B. That's maybe that's the intuition behind this area law.
To mimic temperature.
Exactly. Exactly. Like in the agency thermalization sense. Think of it like some. Basically, you can take Hamiltonian in region C as same as if HA and HB have some homogeneity. You can take the same Hamiltonian in C. Then there's some notion of extending the Hamiltonian. If there is some notion of translation invariance, for example, then you can use ETH and sort of use that intuition to argue it's. I mean, we know the answer, but I'm just saying this is a way to think more physically what's going on with temperature. That you have a lot of that there is this trace RhoAB log RhoAB, which is an entanglement between AB and some purifying bath, which is large. So, this is volume law for a thermal state.
So is there any intuition, like settings at finite temperature, at zero temperature? Is there any intuition where the logs come from? Like what other
For the zero temperature? Sure. I mean,
I know there's a calculation.
No, but it's like it's a scale invariant system. So this is the first time I learned this argument is from a paper by Brian Single. So you kind of use RG-like argument that you have order 1 entanglement from every region which is geometrically kind of is a geometrical series of region B's. You can add order 1 from it. So how many such things exist, like log L number of them, because you're doing RG, right? So in RG, you need to separate the whole thing in some geometric series, right, to have some scale invariant. So then you get order 1 bit of, one bit of entanglement or 1 qubit entanglement from every. Yeah. So you can use that kind of argument to sum up to get log L. That's like the simplest argument, at least for a CFT.
But in higher dimension.
High dimension is same. I mean, for the Fermi surface, it's yeah. So exactly. So there you can again, if you repeat that argument, you get actually area law. You do not get log using the same argument. It's basically like ds over something like ds over d log L is. Yeah, if you look at it as it's also it is curvature expansion. Yeah, so you write it as some sum of curvature terms, then your integration. If it's in 1D, you will get log L, but in higher dimensions, it's not. I think we have sort of again underperformed. So let's see. I mean, I wanted to mention something about this question about separating local from non-local terms. Why is a leading term not? I mean, leading term is boring, we say, and there's something here in the subleading term. How is that? Sounds always a bit kind of disturbing, but how? So that I mean, am I allowed to go over 3 minutes more, or what is the rule here? Okay, so I think it's related to these kind of questions. Let me at least finish that. Okay, I will try. Okay. Sorry?
You're only gonna do 3 minutes, maybe.
Yeah. So this area, so we know that the when we have ground state topological order, right? We define this thing called topological entanglement entropy, like which is less restricted, let's say 2 plus 1D for just to given our restriction of 2 minutes. Okay, so S in the ground state looks like some L minus gamma, which we defined gamma was topological entanglement entropy. And the question is, why is this universal and why is this? So if I want to write S as S local plus S non-local, why do I identify gamma with non-local, right? It's not obvious. So same thing for negativity, right? We will do that next time. We will use negativity, the fact that it's area law, we can write the same thing, En as En local plus En non-local. Anyway, so we will write it as some L minus gamma, and we will again do the same argument. So that argument is general, it doesn't matter it's for this or this. So let's go through that argument. So the argument is that we want to think of local entanglement as coming from, so this is region A, this is region B. We want to sum up entanglement of some local patches. Because it's local, we should be able to think of some short distance entanglement between boundary, which lives on the A side, but boundary lives on the B side, some short distance stuff. So we want to almost like, so we can say S or E local part is some integral of some, if you like, entanglement density, let me call it some F along this boundary. And if you are only interested in the scaling with system size, we should be able to, then the only thing that matters is dependence on the local curvature and so on, and various derivatives, kappa, d kappa, and so on. Because if we can determine this, then by doing integration, we can figure out the scaling. It's like doing Landau theory. You're doing you can think of this some Landau functional for entanglement, and you're doing some series expansion of this in various terms of the dependent curvature in various ways. F I've not defined yet, right? F is non-zero at zero curvature also, right? So I'm just let me finish. So I'm just saying curvature of the boundary between A and B. Geometric curvature. So this is you can draw a circle, this inverse radius of this. So now if you do a Taylor series expansion, so the first term is just a constant, right? So this, when you do integration over this will give you area law. So this is what you were saying, the curvature is zero. So the zero curvature gives you only area law. Now the next term you can write it as kappa, then d kappa whole square, maybe kappa square, and so on, right? So let's just look at these terms. So kappa has a dimension of 1 over length scale. So this should give you, so if let's consider 2 plus 1D, just to be concrete. So this is like L. L is the size of the system. This is like 1 over L integrated over L. So this is like constant, and so on. So then if you look at this, looks like some L plus constant plus 1 over L plus 1 over L square, and so on. So far, so good. Here's the punchline. This is actually not allowed. Why? Because there is a S of A is S of B. Sorry? No, it turns out even for negativity, En of A is same as En of B. As we earlier hinted, I mentioned in the problem that if you do partial transpose over A or B, doesn't matter. Same answer you get.
A plus B.
In this, no. What do you mean A plus B is a pure? No, I'm saying for negativity, A plus B is not a pure state. Even then, E and A is E and B. I mean, negativity is entanglement entropy for mixed state. You mean one of an entanglement for pure states? Yeah, it is a pure state, A union B. But that doesn't. That's the reason A is S B in that case. But I'm just saying that, yeah. So let's use that. I'm trying to say I'm not trying to use that it's a pure state. It's a more general condition. It's even true for mixed states. But for pure state, this arises because it's pure. But I'm saying it's more generally true even for mixed state entanglement measures. So then when you interchange A and B, kappa goes to minus kappa, right? This is a symmetry of the problem. So then all terms which are odd in kappa are not allowed. So this is not allowed. This is not allowed. This is allowed. This is okay. So then you will miss. So one term everywhere. So L plus 1 over L plus 1 over L cube and so on. So this calculation can be done in field theory also. This is, for example, if you look at works by Cassini and Hewitt, where they studied entanglement for, let's say, massive boson for a smooth bipartition, you see this observation there also. There's this missing term. So so if you ever see now a constant, a subleading constant, that means it could not have been obtained by this local contribution. So that's the reason. All right, I think we should stop here. But this is we will use this in the next lecture to motivate topological negativity for that's the one immediate application. If you want to define now negativity, like a long range negativity of mixed states, so then we can use this fact. So if we find a constant, then that will signal a mixed state which is highly entangled or long range entangled. All right, I think we should stop it. Yes.
Along these lines, I mean, there's a construction.
Yeah. So that exactly. That we will do that next time. So if you want to cancel out the local part, you use this either Kitaev-Preskville or Levin-Venn protocol. I mean,
Then it doesn't rely on even if it was not here.
No, but you have to still argue why this was a topological contribution, right? I mean, okay, you can. In sometimes it's implicit that it's something is left over and so on. But this is kind of more. It's at least kind of a more. I don't know. Yeah.
Level 1 step for the TEE it's the same as the conditional note information.
Yeah.
That also appear in the squash entanglement. Is there a relation?
As I mentioned, it's a way to cancel out non-local terms. I mean, it's a way to cancel out local terms. That combination. That combination is a very common combination. Shows up in strong subadditivity, shows up in conditional mutual information, and so on. So because you're trying to cancel this local things. Yeah, it's a very it shows up all the time. Yeah. Questions? No question. Okay, there's a question. I think there's an interference with the. Sorry.
About negativity, like does it grow linearly with time under open system dynamics?
At least numerically, it does. Yeah.
Does it also have PPD?
That I don't know. Yeah. I mean, okay, just to make sure you are. I think it has to be a bit more precise. So you are studying a mixed state with some random quantum channels. That's what you want to do.
Sure. Let's say R. Polarization.
What is R? You mean random quantum unitaries or? If it's a pure state, you're starting with a mixed state or pure state, just to make sure.
With like random noise.
Okay. I mean, most of the time, if there is enough noise, eventually it will become area law, right? Because it does become trivial. Like we know that eventually, if there is enough, most of the time, decoherence, if it is strong enough, will completely kill long range entanglement, right? It will become area law. The interesting question is, can there be intermediate time scale in which is volume law? So I have some numerics where at least there were suggestions that you can get some intermediate time scale which is volume law, then it maybe goes down to area law, but it depends on the protocol. Yeah. Yes. Yeah, I would say so. Yeah. I mean, they're only in A, let's say. It could be maybe they are local observables, but they are such that they sit close to boundary between A and B, but you need to know expectation value of them, right? Even if it is short range entanglement, let's consider like this sudden dead temperature. You're at high enough temperature that the there's really no long entanglement, but there's still a certain dead temperature. So you can ask, how can I not absorb it only knowing the entry matrix of A? So my this picture is that their operators, the way it is hidden is between product operators like OA, OB, where both OA and OB sit close to the boundary between A and B. So that's why it's a short range entanglement, but you can't calculate expectation value of that using only ρA. At least that's the physical picture. Yeah. Yes. More questions? Tomorrow is better. I still have, slowly now recovery mode to get there. I didn't tell you while I was coming here. Anyway,
If you don't have any measures. Okay, if you want to go here. Add measures that actually wait time to get out.